Hi guys, welcome to Science Chomp. Today we're going to be looking at Thermodynamics Part 3, Thermal Processes. Now this is all to do with PV graphs, that's pressure volume graphs, and there's 4 thermal processes to contend with. The first one is what we call isobaric. Iso meaning the same, baric as in barometer, meaning pressure. So this is a PV graph where pressure remains the same. So you have something here and it goes in that direction. The pressure remains the same. Now in this situation we can actually work out the work done by doing pressure, normally it'd be pressure P delta V, but in this case, ignore that. What we've got to do is work out the area under the graph. So it's all of that area here under the graph. So it's, you know, base times height basically. That's what we would do for isobaric things. On a PV graph, work done is area under the graph. And in the case of this, we're using the first law of thermodynamics, and that is delta E, change in internal energy or thermal energy, is the heat minus the work done. That still rings true for this thing. Our next thermal process is isovolumetric. Iso meaning the same, volume meaning the volume. So if you have your PV graph, your volume does not change. So you start off here and you're going upwards in this direction. Now, when you've got this thing happening, because the volume isn't getting any bigger, if you have a piston, this situation is not happening. Therefore, there's no work done at all. Which means, no work done at all. Which means, when you have your delta E is Q minus W, if W is 0, that means delta E is Q. And that would be isovolumetric. Our next one is isothermal, which basically means constant temperature. If you remember back to your Boyle's law, you remember that the graph for Boyle's law goes a little bit like this, where you have P and V. Essentially, your thing is going downwards in that direction, your cylinder gas thing. Okay, P1 V1 is equal to P2 V2. Now, because it's at constant temperature, there is no change in thermal energy, which means delta E is equal to 0. So when E is equal to 0, you end up with a situation where it's Q minus W like this, where this is heat and this is work done. So you put that onto the other side, you end up with W equals Q. Or, you know, in the textbook it says Q equals W. It's the same thing. Q, which is the heat, is equal to the work done. An example of this thing is a weather glass, where the temperature doesn't change, but the volume does, and the levels of the thing keeps going up and down. Our next thermal process is adiabatic process, and this is without loss or gain of heat. That means Q, which is the heat, is equal to 0. There is no heat. Usually what happens here is there's no time for thermal energy to flow in or out, and generally the system is very well insulated, and as I said, the process is super rapid, so there's no time for heat to flow. Okay, now just because heat doesn't flow doesn't mean that things can't get hot and cold. You do get adiabatic cooling and adiabatic heating. Now during adiabatic cooling, what happens is, like, your gas, it expands rapidly. So gas expands rapidly, and as it comes out, it just cools things down. So if you let air out of a tire, you'll notice it's super cold as it comes out. Adiabatic heating is the opposite. If you have a piston, like a bicycle pump, and you keep pumping the thing, it gets like very warm. Reason being, there's no time for thermal energy to flow. So all of that work done gets converted directly into energy. When we take into account delta E is Q minus W, what's basically happening, if this is 0, delta E is equal to minus W. So basically what's happening is the work done gets converted into energy, and that's exactly what's going on. Now, why is this? Well, if you cast your mind to Gay-Lussac's law, and Gay-Lussac found this situation over here, where you got pressure and time, and P1 over T1 is equal to P2 over T2. Okay. Now, what does that mean? Well, the temperature, when the pressure is very low, is going to be low, and when the pressure is high, the temperature is going to be high. We can also combine it with this. It becomes a very steep hyperbola with your PV graph, right? So as the pressure gets higher, basically the temperature gets higher. That's more or less what's going on. Or as the pressure gets lower, the temperature gets lower as well. So that's adiabatic cooling and heating. And we can demonstrate it as well. Like if you like breathe on your hand slowly, you can feel it's quite warm. Whereas if you purse your lips and blow hard, actually the air expands so rapidly, there is no time for thermal energy to flow in or out, and that movement of the air causes cooling down. Okay, so that's all of the thermal processes right there. We've got number 1 was isobaric, isovolumetric, isothermal, and adiabatic. Thank you very much for watching, and goodbye.